Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we will talk about our next functional group, which is a thiol. And so thiols are organic compounds that contain a sulfhydryl group, or just S and H. And so if you guys are trying to look at how the sulfur is going to bond with hydrogen, it's merely just a single bond. And so if we have a single bond between the sulfur and hydrogen, we will have our sulfhydryl group. And if that sulfhydryl group is covalently bonded to one of the carbons in an organic compound, then this whole substance is going to be classified as a thiol. And so one example of a thiol is ethane thiol. So in this scenario, we have a 2-carbon organic compound in which the first carbon is covalently bonded to the sulfur in the sulfhydryl group. So very similar to what we've discussed in prior functional groups, we're going to go ahead and determine the electron and molecular geometry for the sulfur, the central heteroatom in this functional group. So if you count the number of electron groups, whether they're lone pairs or they're involved in a bond, a covalent bond, here we have 1, 2, 3, 4 groups of electrons. And so the electron geometry is going to be tetrahedral. So when we're talking about the molecular geometry, we're considering the combination of lone pairs and the number of groups of electrons that are involved in a bond. And so if we're looking at this image, here we see 2 lone pairs and 2 bonds. And so that combination is going to tell us that the molecular geometry for this sulfur is going to be bent. And so taking both of these items into consideration, we can go ahead and determine that the angle with respect to sulfur is going to be less than 109.5. And so the reason why it's 109.5 is because that's the bond angle for tetrahedral geometries, and it's less than 109.5 because our molecular geometry is bent. Also, if you draw in the lone pairs that's surrounding this sulfur atom, these electrons are going to repel each other. And when they repel each other, it's also going to push these bonds closer to each other, therefore producing a bond angle that's less than 109.5. Okay. And so overall, the shape around the sulfur atom is going to be bent. And so what that tells us is that if we're trying to represent these thiols in the skeletal structure, and if you wanted to expand the functional group to include that of sulfur and hydrogen, to include the bond between sulfur and hydrogen, you're going to want to make sure that you kind of bend it a little bit to mimic this idea of a 109.5 bond angle. And so here, since this is a 1,2 carbon compound, we're going to go ahead and represent those 2 carbons as a point. And there's my covalent bond. And then since this carbon right here has a bond angle of 109.5, then that's going to tell us that we're going to have to bend the bond that leads to sulfur. And if you guys wanted to show the bonding between sulfur and hydrogen, you're going to have to bend that as well to represent that 109.5 degree. It doesn't have to be exact. And so this is one way for you guys to depict this sulfhydryl group using the skeletal structure. Now, typically, we combine these together to kind of shorten the amount of time it takes to write this functional group. And so we commonly represent the sulfhydryl group as just SH. And so typically the bond between the S and the H and the lone pairs of the sulfur is ignored, as you guys saw in alcohols. However, you just have to remember that there are two lone pairs on sulfur, much like there were two lone pairs on the hydroxyl group, the oxygen in the hydroxyl group. All right. And so the next thing that I want to cover is the physical properties of sulfhydryl groups. And so if you guys look at the periodic table, you'll notice that sulfur and oxygen belong to the same family. Same family, same group. And so if you guys are looking at the periodic table, oxygen is on top and sulfur is right at the bottom. And so some of their properties might be similar, but since they're different atoms completely, some of their properties might be are going to be completely different. And we're going to go ahead and explore that. And so because hydroxyl groups are very similar to that of sulfhydryl groups in terms of structure, it only makes sense for us to compare the physical properties between these two. Okay. And so I'm going to go ahead and just quickly scroll down here so that we can see this chart. And so looking at this chart, it's describing the boiling point, which is a physical property of thiols, and the boiling point of alcohols. And so for us to better understand what's going on in this chart, I'm going to go ahead and highlight the prefix meth, eth, bute, meth, eth, bute. And so it looks like we're comparing thiols with the same number of carbons to that of the alcohols. So this is a 1 carbon thiol, a 2 carbon thiol, a 4 carbon thiol, 1 carbon alcohol, 2 carbon alcohol, and a 4 carbon alcohol. Now, if you guys are looking at their boiling points across the board, we go from 6 to 65, 35 to 78, 98 to 117. And so it looks like overall the boiling point for thiols is going to be less than that of alcohol. So I'm just going to put a less than sign. Okay. I'll carry it over here. So thiols are going to have its boiling point is going to be less than that of alcohols. And so the same trend actually holds true for the melting point. And so when you guys are comparing these thiols and alcohols, you want to make sure that you guys are comparing it having the same number of carbons or molecular weight or size. Okay? So if you guys are comparing, for example, 1 butane thiol, a 4 carbon thiol, to a 1 carbon alcohol, that trend, this idea of alcohols having a greater boiling point than thiols, it's going to break down, right? And so whenever you guys are making these trends between boiling points and melting points, you want to make sure that you're comparing the melting points and boiling points of thiols and alcohols that have the same number of carbons, same shape and size, or similar shape and size, similar molecular weights. So that way you can only you can cancel out these carbons, and you can cancel out like all these other factors such as number of carbons, shape and size, and that leaves you with only the functional groups that's going to be different between them. And so it looks like we have a huge increase in boiling point between thiols and alcohols. And so why is that? So to better understand this, I'm going to go ahead and use some white space over here. And what I'm going to do is I'm going to draw the interaction between two thiols and two alcohols. And so I'm going to go ahead and use that ethane thiol. And so I'm going to go ahead and duplicate this. And then I'm going to go ahead and draw, maybe I'll just duplicate this also. Oops. Okay. Shoot. All right. So for us to better understand the difference in physical properties such as melting point and boiling point, when we're comparing organic compounds of similar number of carbons, shape, size, etc., we're going to have to look at the intermolecular forces that's occurring, between these sulfhydryl groups and these hydroxyl groups. And so let's go ahead and revisit hydroxyl groups first. So we know that oxygens are highly electronegative. So they have high electronegativity. And if you were to calculate their difference in electronegativity with that of hydrogen, the change in electronegativity is going to tell us that it's going to be a polar covalent bond. And so that informs us that there's going to be a net dipole pointing towards oxygen, making this oxygen partially negative and this hydrogen partially positive. And so since this alcohol that I just kind of moved down at the bottom still has the same bonding pattern, same number of atoms and elements, then this will also have a permanent dipole that's pointing towards oxygen, such that this oxygen is going to have a partial negative charge, and this hydrogen is going to have a partial positive charge. And so when these two molecules interact, so we have negative interacting with a positive, the negative here interacting with a positive there. These interactions, they're known as hydrogen bonds. And hydrogen bonds are very strong bonds. Or, well, not strong bonds, they're very strong interactions. So the word bonds and hydrogen bonds is kind of like, it's kind of misleading. It's not an actual physical covalent bond. It's more of an attraction. Okay. And so when you guys are trying to connect this to this idea of boiling point, for the liquid to go from, for the substance to go from liquid state to gas state, its temperature is going to have to be higher than the boiling point. And so if you have intermolecular forces, such as hydrogen bonds that induces, strong attractions between two of these alcohol molecules, then that means that for them to separate, for these two molecules to go from liquid to gas, you would have to invest a lot of energy to break them apart. So you need high energy to break these hydrogen bonds so that the molecules can go from liquid state to gas state. And so we're going to go ahead and take that idea and apply it to sulfhydryl groups. Okay. And so for sulfhydryl groups, if you calculate the change in electronegativity between sulfur and hydrogen, the change in electronegativity is very close to 0.4. And so that tells us that this bond is going to be non-polar covalent. And if we have a non-polar covalent bond, then this is informing us that this bond right here, I'm sorry, let me take a step back. So that since the bond is non-polar covalent, this is telling us that there's no net dipole. Okay. And so if there's no net dipole, then that's when these two molecules interact, these interactions, these interactions are mostly going to be weak. And the most common weak interaction is going to be London dispersion force. And so since there's no net dipole, these sulfhydryl groups are not able to, explore these interactions, or it's not able to explore stronger interactions such as dipole-dipole. Okay? And so because London dispersion forces are weaker interactions or weaker attractions between two molecules, it doesn't require a lot of energy to break them apart. So and so if you don't really need a lot of energy to break them apart, then that means their ability to go from liquid to gas, their ability to surpass the boiling point is going to be lower than that of alcohols. And so if you don't need a lot of energy to break these interactions, then it will be able to enter its gaseous phase at a lower temperature compared to interactions or attractions between molecules that are stronger. And so going through this explanation, hopefully you guys get a better appreciation as to why thiols overall have a lower boiling point and melting point than similar alcohols. And whenever you guys are using this word or seeing this word similar, the criteria that they're talking about is, once again, the same number of carbons, similar shape, size, and molecular weight. Okay. So what we're trying to do is we're trying to cancel out all these other external factors so that we can primarily look at the effect of the functional groups on the melting point and boiling point of these organic compounds. And so it's crazy. I mean, like, we only just changed one element. We switched out a sulfur to an oxygen or an oxygen to a sulfur, and look at how different their boiling points are. Okay. And so it kind of shows, this exercise just kind of demonstrates like this domino effect of concepts that we've learned in the first part of general chemistry and how it's applied to these organic compounds. Okay. And so the next thing that I want to discuss is the nomenclature for thiols. So now that we have an idea of what thiols look like and an idea of their physical properties, we're going to go ahead and discuss how to name thiols. All right, so looking at these, general rules to name a thiol using the IUPAC system, we're going to find the longest carbon chain, and then we're going to name the parent hydrocarbon chain as an alkane. And so it's not necessarily an alkane, there can also be an alkene and an alkyne, but the main idea is that you're first trying to name it as if it's an alkane. And if there's a double bond, then you would change the ending from ane to ene. And if there's a triple bond, then you guys are going to change the ane ending from ane to yne. Okay. And so after you guys have the correct parent name, you're going to go ahead and add the suffix thiol. And so, very similar to alcohols, you want to convey to the reader what carbon number contains that thiol. Is it going to be carbon number 1, carbon number 2, carbon number 3? The list continues. And so, since thiols is our functional group for this set of organic compounds, when we're numbering our carbon chain, we want to give the thiols the lowest possible value. There's a couple of exceptions to this, and that's going to be methane and ethane. And so if you guys look at the number of carbons in methane and ethane, it's just only 1 carbon and 2 carbons. And so this is an example of methane thiol. So looking at this 1 carbon compound, usually you would have to tell the reader what carbon number this functional group is found in. However, for a 1 carbon compound, there's only one way to attach a thiol to this 1 carbon compound. And so if there's only one way for you guys to attach that functional group to that specific organic compound, then what you want to do is you want to omit communicating that it's going to be on carbon number 1, right? And so what we want to do is we want to reduce redundancy in the nomenclature of this thiol. And so if you were to say 1-methane thiol, it wouldn't exactly be wrong. I mean, you're still communicating that this thiol is on this thiol right here is on carbon number 1. However, since methane only has one carbon, it's just being redundant. And so that's an example of why the carbon number 1 is omitted on methane. And the same idea can be applied to ethane. If you guys are looking at ethane thiol, if you place this thiol on this carbon, that's one way to place it. But if you place this thiol to this carbon, and if you were to write out its chemical formula or chemical structure, so I'll go ahead and do that real quick. So I'm just going to write a reflection. Remember that you have to make sure that the carbon does not break its octet rule. And so when we're adding this thiol onto this carbon that's on the left, we have to make sure that the carbon only has enough bonds so that it fulfills its octet rule. Okay. And so if we're adding a thiol on the carbon on the left, then we don't need 3 oxygens. We'll just need 2, I'm sorry, not oxygens. We don't need 3 hydrogens. We'll just need 2 hydrogens. Okay. And for the carbon on the right, originally it had 2, but in this case, if we're putting the thiol, the sulfhydryl group on the carbon on the left, then that means we need to increase the number of hydrogens on this carbon that's right here on the right. So long story short, if you guys are looking at, I'm going to erase all my scribbles here. If you guys are looking at this structure for ethane thiol, and if you guys are looking at this structure of ethane thiol, they're both the same. And so really, technically, there's only one way to place a sulfhydryl group on an ethane. Okay. And because there's only one way to place a sulfhydryl group on ethane, you're going to go ahead and omit the 1 from its name. So you don't need to describe or tell the reader where that thiol is. It's implied that it's going to be on carbon number 1. Now, if you guys are looking at this example, here we have a 3-carbon compound. And if we were trying to follow the rules to naming this specific thiol, the first step is to find the longest carbon chain. And so the longest carbon chain is going to be 1, 2, 3. And that's going to inform us that we're going to use prop as its prefix. And so since they're all single bonds, this is going to be propane. Now, according to the rules, we don't really need to change the name of the alkane, much like what we did with alcohols. Right? So for alcohols, we drop the E in the ane and then add OL. So we get like ethanol or something like that. And so here in this case, we just write the name of the parent, and then we're going to add that thiol at the very end. And so what we get here is just propane thiol. Okay. Now, for a 3-carbon compound, there's actually 2 ways to place this thiol. You can place it on either end, so I can place the thiol here. I can place my sulfhydryl group on the ends, so I can place the sulfhydryl group here or here. Okay. And so either one of those locations that I've starred, it would still give us the same name, propane thiol, or specifically 1-propane thiol. However, if we were to place the thiol, or this sulfhydryl group, in the middle, that wouldn't be one propane thiol at all. That would be two propane thiol, and I think I have an example of that here. Okay. So here in this case, we have 1, 2, 3 carbon compound with a thiol on the second carbon. And so overall, the name of this is 2-propane thiol. And so because there are two different ways to name a 3-carbon organic compound with a sulfhydryl group, you must indicate or you must communicate to the reader the carbon number of where that sulfhydryl group is covalently bonded to, or where that sulfhydryl group is located on the carbon chain. Okay. All right, so let's go ahead and look at this next example. So here I have a 2-carbon compound, and it looks like I have 2 sulfhydryl groups. And so I'm going to go ahead and name this piece first. So a 2-carbon compound is simply ethane. And since I have a sulfhydryl group, I'm going to go ahead and add in thiol. But since I have 2 sulfhydryl groups, I'm going to go ahead and describe that I have 2 of them by saying ethane dithiol. Okay, all one word. And so for this ethane dithiol, if you have 2 thiols, there's actually 2 ways for you guys to put those sulfhydryl groups on this 2-carbon compound. And so I'm just going to go ahead and draw the skeletal structure. And so if I have sulfhydryl groups on both ends of that 2-carbon compound, so here's my 2-carbon compound, then I have a sulfhydryl group here, and I have another sulfhydryl group here. Okay. And so this isn't the only way for me to represent a dithiol that contains 2 carbons. Another way is for me to place those 2 thiols on the same carbon. Okay. And so notice that this structure, the one at the bottom, is going to be completely different from the one at the top. And so since they're completely different with respect to each other, that ethane rule that I discussed here does not hold true. Okay. And so this rule, this methane ethane, and you're going to omit the 1, is only for a mono thiol, right? Or just one sulfhydryl group on an organic compound. And so here, in this example, there's 2 ways for me to represent where those sulfhydryl groups are going to be covalently bonded to the carbon. So long story short, these are constitutional isomers. And because I have 2 constitutional isomers, or well, I'll just leave it like that. That tells me that I need to communicate to the reader the numbers. So what carbon number are those sulfhydryl groups covalently bonded to the carbon? Here in this case, it's carbon 1 and carbon 2. So the main point that I was trying to get at was that you would have to tell the reader or your audience that those sulfhydryl groups are on carbon 1. One of them is on carbon 1 and the other one is on carbon 2. If you were to name this isomer, then you would have to say 1, comma 1 dash ethane dithiol. Okay. All right. So let's go ahead and look at another example here. If we have a 4-carbon compound, then we would use bute or butane, since it's a single bond between those 4 carbons. So we will have butane, and we're going to go ahead and communicate to the reader that we have a sulfhydryl group, and we're going to go ahead and do that by adding the word thiol at the very end. And so we want to communicate to our audience what carbon number that sulfhydryl group is on. And so remember that these sulfhydryl groups, these functional groups, are going to get the lowest possible carbon number when you're trying to number your carbons from left to right or right to left. And so if you're numbering it from left to right, I have 1, 2, 3, 4. And if you go from right to left, I have 1, 2, 3, 4. And so it looks like the numbering system going from left to right is wrong. And the numbering system going from right to left is correct, because we would get a lower carbon number if we numbered our chain from right to left. And so now that we know our numbering system for our carbon chain, then we're going to go ahead and add a 1 in front of butane, so 1-butane thiol, to communicate to the reader that this sulfhydryl group is on carbon number 1. And so here, it looks like on carbon number 3, we have a methyl group. So this is going to be 1-methyl 1-butane thiol. Okay. All right, and so that's how you would name this specific compound. Nope, nothing over here. All right, so let's go ahead and go through, I think there's 4 more molecules. So let's go ahead and go through these last four examples. So step number 1, find your longest carbon chain. So here we have 1, 2, 3. Now, if you had said, oh, I don't want, oops. So here we have 1, 2, 3. Let's just say that, oh, we don't want that one, we want this one. It'll still give you 3 carbons. So it doesn't matter if you go from left to the right or from the bottom to the right. So now that we have determined the longest carbon chain, we know that this is propane. If you're looking at the skeletal structure, so looking at the skeletal structure is actually much easier to determine if it's an alkane, alkene, or alkyne. For the condensed structure, you're going to have to count the number of hydrogens, or maybe write the expanded form of this structure, so that way you can see whether or not you have single bonds or if there's a double bond present. All right, so since we have a 3-carbon compound, we're going to say propane, then we're going to go ahead and describe this sulfhydryl group as a thiol. We need to communicate to the reader where this sulfhydryl group is located on the carbon chain, and in this case, it's going to be on carbon number 1. So we're going to number our chain from right to left, because numbering it from right to left will give us the lowest carbon number for this functional group. And so now that I've determined that this is 1-propane thiol, I just need to describe the rest of my substituents. And so in this case, I have a methyl group on the second carbon. So I'm going to go ahead and write 2-methyl. -1 propane thiol. And that's going to be the name of this organic compound. All right, so this is something that's new to us. Here we have a ring. And so how do you name a ring that contains a sulfhydryl group? And so very similar to what we've learned in prior lecture videos, we want to describe the parent chain. And since it's a ring, we're going to have to add the word cyclo. So we first need to know how many carbons there are on this ring. So here we have 1, 2, 3, 4, and 5. And so I have a cyclopentane. And since there's a sulfhydryl group on that cyclic ring, I'm going to say cyclopentane thiol. Now, remember that for rings, wherever that functional group is, it's very similar to our cyclic alcohols. Wherever this sulfhydryl group is located in the ring, that carbon that shares its bond to that sulfhydryl group is automatically going to be carbon number 1. And so for cyclic sulfhydryl groups that's on a cyclic compound, you do not need to inform the reader the carbon number of where that sulfhydryl group is located, because it's implied that it's always on carbon number 1. And so the only thing that's left to do is to describe the other substituent. And so we want to number our ring such that the next substituent is going to have the next possible lowest carbon number. And so if I were to number it counterclockwise, I would get 1, 2, 3, 4, 5. If I were to number it clockwise, I would get 1, 2, 3, 4, 5. And so in this case, since my substituent, which is a methyl group, is on this specific carbon, I'm going to go ahead and compare these two numbers. And so since this number 2 is lower than 5, that tells us that the numbering system that's in blue, the numbering system that went counterclockwise, is incorrect. And so my final answer here is going to be 2-methyl. Oops. Cyclopentane thiol. And since I don't need to put a number in front of cyclopentane because for cyclic rings, that functional group is always on carbon number 1, I'm just going to go ahead and merge those two pieces to create one specific name for this organic compound. So it's 2-methyl cyclopentane thiol. All right. So let's go ahead and talk about how to name sulfhydryl groups that is present in an aromatic compound such as benzene. And so it's been some time since we've kind of discussed, benzenes and naming benzenes and all that stuff. But if you guys recall, this conjugation of double single bond, double single bond, double single bond, that's going to represent that aromatic compound, which is called benzene. And when that benzene has a methyl, when that benzene has a methyl group that's attached to it, we can go ahead and name this whole section toluene. So what we're going to do is we're going to use the common root name for a benzene with a methyl group that's attached to it. Oops. And so after we've named the parent chain, we're just going to simply add thiol. So we have toluene thiol. And since we have two thiols, we're going to have to modify what I just wrote down and make sure that I write di to communicate to the reader that I have two thiols. The last thing that I need to do is communicate what carbon number those thiols are found in. And so in this scenario, since we're naming, since we're using the methyl group and the benzene ring, and since we're looking at that section as one entity, wherever that methyl group is, that's going to be carbon number 1. And so if we number this counterclockwise, is number 2, number 3, number 4. So it looks like we have a sulfhydryl group on carbon 3, sulfhydryl group on carbon number 4. So we're just going to go ahead and put in 3, 4. Three, 4 dash toluene dithiol. Okay. So that's going to properly communicate where those sulfhydryl groups are found on the toluene. Okay. All right, so let's go ahead and look at our last example. How would we name a sulfhydryl group in which a double bond is present? So once again, we're going to go ahead and count the number of carbons, 1, 2, 3, 4, 5. So that's the longest carbon chain. And so if we have a 5 carbon chain, then, and it's not cyclic, it's acyclic. So therefore, we're just going to simply say pentane. Okay. However, since we see a double bond, we can't say pentane, we have to say pentene to signal the reader that there's a double bond present in my organic structure. And it looks like I have a thiol here, so I'm just going to go ahead and put in a thiol. So I have pentene thiol. And so the next thing that you want to do is you want to convey to the reader what carbon number that sulfhydryl group is found. And you also want to convey what carbon number that the double bond will start. And so let me do this in a different color. When you guys are communicating to the reader, the audience, the carbon number in where the double bond will start, that number is going to go in front of the pentene. And so to communicate to the reader or your audience or whatever, the carbon number in which the sulfhydryl group is found, you're going to have to put a space between pentene and thiol. And then you're going to have to add the 2 dashes. And I'm going to put a question mark right in between them because I don't know my carbon number just yet. And so the main point that I'm trying to convey is that the carbon number to describe the position of where that sulfhydryl group is found is going to be between pentene and thiol. And so to kind of fill in these question marks, so to speak, we just need to we need to figure out our numbering system for this organic compound. So keep in mind that your sulfhydryl group gets the priority. So you want the lowest carbon number. Okay. So between an alkene and a thiol, or an alkene versus any functional group, your functional group is always going to get the priority. It's always going to have the lowest carbon number. And so that means that if we number it from left to right, I have 1, 2, 3, 4, 5. If I go right to left, 1, 2, 3, 4, and 5. Since we want the lowest carbon number for the sulfhydryl group, then that means the numbering system from left to right is preferred versus right to left. And so here in this case, I'm going to go ahead and erase this question mark now that I've figured out my numbering system, and I'm going to put 2 thiol. And now that I've figured out my numbering system, I'm going to go from left to right, so 1 to 2, 2 to 3. And it looks like on the second carbon, that's where my double bond starts. So I'm going to say 3 pentene. And that would be the name of this organic compound, 3-pentene-2-thiol. Okay. So hopefully after going through those brief examples, you guys have an idea of how to name these sulfhydryl groups under different situations, right? So the first one, it was just a typical alkane. The second one was a cyclic ring. The third one was a benzene ring. The fourth one involves a double bond. And you guys can apply the same logic for triple bonds as well. And so instead of it being 3-pentene, it can be like 3-pentyne or something like that. But the main idea is that the carbon number is going to be between the name of the double bond and the functional group, in this case, the sulfhydryl group. All right, so now that we've discussed these physical properties for thiols and the nomenclature for thiols, let's go ahead and discuss where these thiols are present in. And so, as you might have guessed, here there are 2 images of a skunk. And so the substance that the skunk spews out contains a mixture of thiols, these organic compounds that contain a sulfhydryl group. And so when you're analyzing these organic compounds that attributes to that really foul odor that we would associate to skunks, it's coming from a combination of 3 different sulfhydryl groups or 3 different thiols. And so here we have a sulfhydryl group, here we have another sulfhydryl group, here we have another sulfhydryl group. So it looks like 38 to 44% of that liquid mixture that produces that foul odor that we associate with skunks is going to be E2-buten 1-thiol. Okay. And so we're not going to talk about this E and Z nomenclature this semester. We're going to go ahead and just leave it as that. But 38 to 44% of that liquid mixture is composed of this specific organic compound. And then here you have 18 to 26%, 3 to 12% is going to be 2-quinoline methane thiol, right? 3-methyl 1-butane thiol. And so typically when we discuss thiols or sulfhydryl groups, it's associated with more strongly, they produce strong odors in terms of aromatic compounds. And so thiols are also found in common foods that we eat, such as oysters and cheese. And so part of that very strong odor, that very strong smell that we get sometimes from cheese, depending on the sharpness of the cheese, if you will, is going to be methane thiol. Same thing with oysters. And so garlic and onion, that more that strong odor that we get from onion and garlic, it's coming from another organic compound that contains a sulfhydryl group. So in this case, we have 1-propane thiol in onions and 2-propene 1-thiol, which is going to be garlic. So it's pretty interesting. We see all of these different types of organic compounds that's going to elicit some type of biological response. And so when we're smelling these substances, methane thiol, 1-propane thiol, et cetera, it elicits a different biological response that we attribute to onions, cheese, oysters, and garlic, and skunks. So one common use and one common industrial use for organic compounds that contain a sulfhydryl group is signaling a potential gas leak. And so propane in itself, so for example, summer's coming up, people tend to want to go outside, barbecue, etc. So if you guys are using propane to barbecue your meat, propane itself is odorless. And so if there is a leak in your propane tank, you wouldn't necessarily know. And so what these organic chemists do is that they modify that propane so that it would induce some type of smell that would signal to us as human beings that there could be a leak in that propane tank. Okay? And so overall, these sulfhydryl groups, they can act as odorants for natural gas. And that's beneficial to us, right? We want to know if there's a gas leak. And so the last thing that I want to discuss in this lecture video is oxidation and reduction reactions for thiols. And so we've discussed oxidation reduction before, but we're going to go ahead and look at it with respect to sulfhydryl groups. And so before I scroll down at the very bottom, I'm going to just write some stuff here in this white space. And so if you guys have two organic compounds, and by the way, the squiggly line, if you guys recall, represents that this functional group, this sulfhydryl group, is going to be bonded to some type of carbon chain. So it's kind of like an R group, and we don't really care what it is. And so if you guys have two organic compounds that have a sulfhydryl group, it can undergo oxidation and reduction. And so if you were to recall from our brief discussion of oxidation with respect to organic chemistry, one of the things that happens in oxidation is loss of hydrogens. And reduction would be gain of hydrogens. And so if we're looking at this specific structure here that I drew, if oxidation is being performed, so I'm going to go ahead and write it with a bracket O. So this bracket O is representing oxidation. So we're going to oxidize somehow. We're going to add a specific catalyst that will catalyze the oxidation process. So if we oxidize these two sulfhydryl groups, what's going to happen is that these hydrogens are going to break apart. Oh, let me zoom in here. Okay. So if you recall, a covalent bond is composed of two electrons. And so if during the oxidation process, that covalent bond between the sulfur and the hydrogen is lost, these hydrogens are going to go somewhere else, right? So we don't really care about where they go. They'll probably be attached to that oxidizing agent. And so what you're left with are these two sulfur atoms. And so the electrons between those two sulfur atoms will be shared, forming a covalent bond between those two sulfur atoms. And so another effect of oxidation with respect to sulfhydryl groups is a gain of sulfur to sulfur, right? So you're going to gain a bond between sulfur to sulfur. Now, if you're talking about reduction, reduction is when you have, these two sulfur atoms that's already covalently bonded. But what's going to happen is that some type of catalyst is going to destroy this single bond, and then it's going to add hydrogens to those sulfur atoms, and those electrons between hydrogen and sulfur will be reformed. And so when a reduction of thiols occur, you're going to gain hydrogens. However, you're going to lose a covalent bond connection. Gain or lose. Okay. So here you're going to lose that covalent bond between those two sulfur atoms. And so why is this relevant? In your body, there are 20 amino acids. And one of those amino acids, called cysteine, contains a sulfhydryl functional group. And so these sulfhydryl functional groups, when an oxidation reaction occurs, the hydrogens, very similar to what I kind of drew a while ago up here, they're going to be extracted some way, somehow. And the electrons that's left over between the two sulfur atoms, they're going to bond to form a covalent bond. And this covalent bond is known as a disulfide bond. It's simply because you have two sulfurs. And so this is really relevant in terms of protein chemistry, just because a disulfide bond is the only covalent bond that can be formed amongst the interactions of these 20 amino acids that's in your body. And so these amino acids will act as the subunit for a protein. So think about amino acids like Lego blocks or Lego bricks. And the castle, the combination of all these different Lego bricks to form the castle in itself is that macromolecule, that protein, whatever it is. And so most of the interactions among amino acids are, intermolecular forces. So, compared to a covalent bond, they're all weak interactions compared to a covalent bond. So things like London dispersion forces, dipole-dipole, electrostatic, hydrogen bonds, all of those intermolecular forces are commonly present in, it's commonly present when the side chains of the amino acids interact with each other in this protein complex. However, there's only one way to form a permanent bond between two amino acids through their R groups, which is in this case a sulfhydryl group, and that's cysteine. And so another reason why this is relevant is, let me see here. So antibodies, that's a hot topic these days. So antibodies, they are formed by having this one long polypeptide being cut and modified in certain ways. And overall, what will hold these pieces of protein strands to make the antibody is a disulfide bond. And so that disulfide bond, that permanent covalent bond between the sulfur atoms and a cysteine amino acid is going to ensure that the shape of the antibody does not change. Okay. And so, a rudimentary image of an antibody kind of looks like this, where all of these blue lines that I'm drawing represents the disulfide bond. And the pieces, the lines in pink, it's representing this polypeptide chain. And the connection of those polypeptide chains to form that antibody is only made possible through the oxidation of these cysteine amino acids to form that covalent bond. Okay, all right. And so that's pretty much it for oxidation and reduction of thiols. It's pretty simple. It's not very complicated like the oxidation and reduction of alcohols. So just keep in mind that for oxidation and reduction of thiols, it's not carbon-oxygen that's being lost or gained. It's sulfur to sulfur. So you're either gaining a sulfur bond or a bond between the two sulfur atoms, or you're losing that bond between two sulfur atoms. But this idea of loss of hydrogens and gain of hydrogens still is a common theme between oxidation and reduction, between sulfhydryl groups and hydroxyl groups, okay, thiols and alcohols. All right, so that's pretty much it for thiols. The next functional group that we're going to discuss are aldehydes and ketones. Okay, so I'll go ahead and see you guys in the next lecture video.